Here's a quick little video that allows us to put together some concepts that we talked about in Chapter 3 with damped harmonic oscillators with some new concepts of the extended linearity principle and forced harmonic oscillators. So we're going to look at some qualitative implications of the extended linearity principle. So let's remember our good old damped and unforced harmonic oscillator, y double dot plus py dot plus qy equals 0. And again, right, this is the mass, this would be this damping thing, the damping coefficient, this would be the spring constant, and we divided everything by the mass to just make things look a little nicer. Well, we know that if something is damped, then we know that P is strictly greater than 0, because P is B over M. And Q is also strictly greater than 0 if it's damped. And again, most of the time we are looking at damped harmonic oscillators. Undamped harmonic oscillators just don't really exist, more or less. Everything is at least a little damped, even if we try to make it as undamped as possible. So if this is the case, remember back to your trace determinant plane. Remember back to what your guess is going to look like. Remember back to what your quadratic formula is going to tell you about your eigenvalues. Putting all that together, we know this is always going to be a sink. The only way it's not a sink is if P was 0 and there was no damping, and then we'd have a center, right? So we know this is always a sink. We know solutions always tend to 0. As time goes on, our solutions are going to 0. Let's call y sub h for homogeneous our solution. So we know that. So now let's go to this new thing that we're talking about, our forced harmonic oscillator, which is just the same thing as the damped harmonic oscillator. The only difference is we're not leaving it alone anymore. Maybe the table's shaking, maybe someone's moving it, maybe there's an earthquake, maybe there's wind, but there's some kind of external force being applied to the system, being applied to this thing that is oscillating in some way. We're going to call that external force a function of t, g of t. So the extended linearity principle tells us that any solution of this looks like the homogeneous solution plus any particular solution. So what does all this say about our general solution to the forced harmonic oscillator? Well, if this is going to 0, what's happening to y? Y of t really just kind of approaches the particular solution as t goes to infinity. Okay, so that's going to be pretty interesting, and we can see a couple visualizations of this in the textbook, which I didn't grab the image for, but essentially, if you have maybe you have like a whole bunch of different particular solutions, maybe your forcing function is some kind of sinusoidal forcing function. And then this is your t-axis and this is your y-axis. Well, I don't care what like general solution you have or what initial condition you have, right? Eventually, they're all going to approach that blue line, no matter where you are. Okay, everything's going to approach that particular solution over time. And so we can use that to do a lot of analysis. Okay, they all approach y p of t. And we'll see that in the examples. We'll call that out in the examples in this section. And then there's a couple of vocabulary things that I do want to tell you about for anyone interested in electrical engineering. But in engineering, oh gosh, we call the particular solution, that yp, the forced response. I say we, I'm not an electrical engineer, just passing on the good word of information. So that is going to be the forced response, its behavior, how the forced response behaves is called the steady state response. And it should be commented, again, we think of steady state, I think kind of intuitively as something that's not changing, a constant. But a steady state response is not necessarily constant. You can see in the example I just drew up here, it could just be constant oscillations where we're not changing magnitude really anymore, or amplitude rather, but we are just kind of grooving. Grooving is still a steady state response. You don't have to be frozen. You can still groove, okay? And then the homogeneous portion of the solution is the natural response or the free response. So you may see these terms fly around. So I wanted to introduce them right here. So we might say that any solution to a forced harmonic oscillator, that looks like this, eventually the natural response dies out. The free response dies out. We showed that right here. And we approach the forced response. We see that steady state response eventually. The behavior of that forced response. Everything's going to approach the steady state solution. Okay, so you may see terms like that. We won't use them too much, but I'll try to incorporate them whenever I can to try to give you a big picture, because I'm a math guy. I like to teach differential equations, but the fact of the matter is differential equations is primarily used in physics and engineering. So I think it's important to not just live inside my own mathematical pure world of, I'm more of an applied mathematician anyway, but I'm still a mathematician. I'm not a physicist. I'm not an engineer. So of course they might think I'm very pure. But trying to incorporate some other things. All right, that's pretty much it. In the next video, we actually have an example. So we get to use some of this stuff. It's going to feel really familiar to stuff that you've done before. So hopefully nothing too new or too crazy. And we get to see some cool graphs to see, actually see what's happening. And we can get past some of the algebra, some of the calculus, some of the notation, and really get an intuitive understanding of how these equations behave. And that's cool. So that'll be in the next video. Stay tuned. Bye-bye.